Hi, Mrs. Greathouse here, working on the second part of 10.2. Today we're going to figure out our mole to volume relationship. You already know moles to count relationship, or moles equals RPs divided by 6.02 times 10 to the 23rd. You already know moles to mass relationship. Moles equals grams over molar mass. So today we'll figure out how we bring in our volume. The mole to volume relationship goes back to one of Avogadro's hypotheses and states that equal volumes of gases at the same temperature and pressure contain equal number of particles. So if we look at this picture here, both boxes have the same volume. They're at the same temperature and pressure, and they both have the same number of particles, in this case 8. We know that the volume of a gas varies with temperature and pressure. Okay, we have very practical applications of this. If you have a wintertime birthday, you probably remember that when you picked up balloons that were blown up at the store, outside the store to take them to your car, you probably noticed that they shrunk a little bit. Okay, what's happening there? The temperature is cooling off the gases in the balloon. The molecules slow down, okay, and the volume of that balloon is reduced. Okay, if you're riding on an airplane, okay, what happens when you ascend and descend? Okay, you feel that pressure, change in pressure, changing the volume of air that is in your ear, okay, and our ears pop. Okay, it's very important then that when we work with volumes of gas in chemistry, we state that it's a certain temperature and pressure environment. We call that standard temperature and pressure, or STP. So when we work with gases in chemistry, it's understood that we're working at a temperature of 0 degrees C and a pressure of 101 kilopascals, or 1 atmosphere. From this, we get our mole-volume relationship. Okay, key point. At standard temperature and pressure, 1 mole, or, as you know, 6.02 times 10 to the 23rd representative particles of any gas occupies a volume of 22.4 liters. Okay, this is called the molar volume. The young lady here is holding a cube that is labeled 1 mole. Okay, that's 22.4 liters, the size of 22.4 liters. That is 1 mole of gas, no matter what gas. Okay, so from this we can get our mole to volume relationship. The volume of a gas equals the moles of gas times 22.4 liters per mole if we're working at standard temperature and pressure. So this is your conversion factor that you'll use for dimensional analysis. Your formula that you'll use algebraically is volume equals moles times 22.4. Okay, let's practice. We'll work with dimensional analysis first. Okay, sulfur dioxide is a gas produced by burning coal. It is an air pollutant and one of the causes of acid rain. Determine the volume in liters of 0.6 moles of sulfur dioxide at STP. Okay, we'll start with dimensional analysis. We have 0.6 moles of gas, and we need to get to volume, which is in liters. Okay, so 0.6 moles. Our conversion factor is 1 mole equals 22.4 liters. Okay, we can cross out moles on the top and bottom. Okay, multiply 0.6 times 22.4 liters, and we get 13 liters of sulfur dioxide. Okay, we need to keep it straight. Volume is in liters. If we go back, mass is in grams. So this is your final answer. Okay, let's try the same problem but with algebra. There's your formula. Volume equals moles times 22.4. Okay, so here's our moles. We need to find volume. So volume equals 0.60 times 22.4. Okay, so that gives us 13 liters of sulfur dioxide. Same answer as last time. Okay, double check yourself. Does this make sense? 0.6 of a mole is a little bit more than half. Okay, is 13 a little bit more than half of 22.4? Sure enough. Good double check. Okay. So while we're talking about volume, let's talk about density, because density is mass for volume. Okay, if we use that volume as liters and mass as grams, okay, we have this relationship. What happens if we multiply that by our conversion factor for a liter of gas? Okay, we can cross out liters, and what's our answer but grams per mole? Grams per mole is molar mass. So we can make a relationship with molar mass, density, and volume. Okay, to simplify that, we can say molar mass equals density times 22.4. Okay, this is another algebraic formula that you need to know. Okay, let's practice that. The density of a gaseous compound containing carbon and oxygen is found to be 1.964 grams per liter at standard temperature and pressure. What is the molar mass of the compound? Okay, so we have to find molar mass. That's our variable. We have our density. We're going to plug that in. Times 22.4. If we crunch that through, we get 44.0 grams per mole. Okay, this tells us that our compound is made up of carbon and oxygen. Can we figure out from what we know about the molar mass of carbon and oxygen what this gas is? Sure we can. We just have to figure out the right combination of carbon and oxygen so that the molar mass adds up to 44. So let's try it. Okay, we know the molar mass of carbon is 12. The molar mass of our oxygen is 16. So let's see, we have to have at least one of each. Okay, so that brings us to 28. What if I add another oxygen? That brings us to a molar mass of 44. So our compound must be 1 carbon and 2 oxygens, which would be our friend carbon dioxide. Okay, that's it for now. More examples in class. See you then.